Hello and welcome to Lecture 8 for the course ECE 1B, Spring 2020. As you see from the title slide, the title of this lecture is String Matching. And the puzzles that lead us to the topic of string matching and its applications are word search puzzles. Okay, so let's get started. Now, word search puzzles are among the simplest puzzles that there are. Not much thinking or insight is required to solve word search puzzles. They're basically more routine activity. There are several variations, and some of these variations are intended to make them a little bit more challenging than the straightforward word search puzzles that even very young people, lower grades in the primary school, can actually do these puzzles. So let's start with the straightforward version, the one shown on the left. A word search puzzle is basically a two-dimensional grid of letters. And then there are a bunch of clues that are written underneath the grid. And these are the words that you should search for. So word search means you're searching for words. And those words can appear in the puzzle in the normal left to right direction, but also they can go from right to left. They can go from top to bottom along a column, or from bottom to top in reverse direction along a column, or they can go diagonally, either in the direction of the main diagonal, like in this direction, or opposite diagonal, anti-diagonal, or they can go backwards. So they can go like this along the main diagonal, or like this along the anti-diagonal. So there are 8 possible directions: left to right, right to left, top to bottom, bottom to top, diagonally, inverse diagonally, anti-diagonally, or inverse anti-diagonal. Okay? So you need to look for these. So for example, if I'm looking for the word agitator, the first one on the list, I find it here. See, agitator. Okay, if I'm looking for the second word, assembly. So typically what I do, I just cross out that word and then cross out this word from the list of words to know that I've made some progress. Okay, then assembly. Basically, there are some techniques that you can develop over time if you do these puzzles. For example, you may notice that assembly has 2 S's. So I look in the grid for 2 S's that appear adjacent to each other. So for example, there's an S here, but there's not a second S in the vicinity. Okay, so I search and I see, oh, there are 2 S's here. And sure enough, that's the word assembly. Okay, well, let's look for another word, pulley. This one has 2 L's. Again, I look for 2 L's. This is a single L. L, L. There are 2 L's here. So that's the word, pulley. Okay, as I said, this is just a matter of spending some time and looking. And You can develop strategies like double letters, as I did for a couple of examples. You can also look for letters that are less common. So for example, if you see that there aren't a lot of, let's say, Z's in the puzzle, and the word contains Z, you first start looking for the letter Z. If there are only a few Z's, and then you decide which one of those Z's belongs to the word. Okay, so that's a straightforward version of the puzzle, which, as I said, it's one of the simplest puzzles there is. Now, this puzzle on the right is a little bit more difficult in the sense that, again, we have a grid with letters. We have a bunch of words. So these are first and last names of actors. And then you're looking for first names and last names. So you're looking for Amy in this puzzle. You're looking for Steele. You're looking for Kevin and Blair and so on. So those are the things that you try to find. The twist in this particular puzzle is that one of the 36 first last names, so there are 18 names, which means there are 18 first names and 18 last names, so 36 things altogether to find. One of them has been left out. And then the solution to the puzzle is basically for you to say which one. Is it, for example, Paul? Is it Young? Which of these 36 items, names, is left out? So this makes it a bit more challenging because, for example, if you're looking for Paul and you look for a while and you don't find it, you're not sure whether you have not looked hard enough, so you may have missed it, or Paul is the missing name there. Okay, so it's just a tiny bit more challenging. Okay, because these puzzles constitute basically useful tools for teaching concepts to children, there are tools. There are websites where you can go, and I've generated this puzzle at this particular website whose URL you see at the bottom of the page. So you go to that website and basically enter your clues. So what I did in this case, I entered the titles of the 10 lectures in this course: binary search, Byzantine generals, without any spacing, cryptography, easy, hard, impossible, and asked the puzzle maker at that site to make me a puzzle that has all of these in it. Okay, well, the longer the clue, like placement and routing, usually the easier it is to find it. So let me count the placement and counting. How many letters? 2, 4, 6, 8, 10, 12, 14, 16, 18, 19. And what is the size of the puzzle? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So let's see if I can find something. Maybe, let's say, malfunction diagnosis. How many letters there? 2, 4, 6, 8, 10, 2, 4, 6, 8, 20. So when the clue is the same size as the width and height of the puzzle, it means the clue in the puzzle extends from one edge to the other edge. So either from top all the way to the bottom, or bottom to the top, across, diagonally. And then you see here malfunction diagnosis. You find it easily on the anti-diagonal, going from top to bottom. Okay, as I said, these puzzles are useful. So for example, if you're teaching some young kids, the concepts of geometric shapes like square, triangle, circle, rectangle, and so on, you can make a word search puzzle that has those words in it and ask the kids to find those words, sort of to reinforce the learning by having them see and find the key words that they need to learn. Okay, so you might want to try this and see if you can find all the 10 lecture topics in this course. So this word search puzzle is from USA Today, the newspaper. It's called Word Roundup. It's not a straightforward word search puzzle in the sense that the clues given are not words. You're not asked to find specific words in the puzzle, but the words are defined by categories. So this makes it a bit more challenging because you don't know what words you're searching for. So in this particular puzzle, you're looking for 7 birds. So you don't know which particular birds. So, it's sort of one step removed from direct search. 5 units of length. And then as you find each of them, you put a check mark in this box. And then when all the boxes are checked, you're done. 4 currencies. 2 things football players wear. And a large gland in the neck. Okay, so let's try to find 1 or 2 things in this puzzle. So let's look for some bird names in the puzzle. I see eagle here. Okay, so I draw a line here or a box around it. And I put a check mark here. Okay, let's find another bird if we can. So for example, loon. So remember, the words can go across, left to right, across, right to left, vertically downward, vertically upward, diagonally top to bottom, diagonally bottom to top, and anti-diagonally top to bottom and bottom to top. So it takes some doing to find all of the words, and then when you complete this, everything is checked, you're done. And if you play this online on USA Today, there's a timer also that tells you at the end how long it took you to complete the puzzle. Okay, so I'm not going to do more on this because that's your question 1. Solve this word roundup puzzle. Okay, and send me an image of the solved puzzle. In other words, at the end, all of these boxes will have been checked, and then the words are either crossed out by a line, like eagle. You can cross it out like this, or you can draw a box around it like this. Either way. So that's your question 1. And then question 2, I'm asking you to build a word roundup puzzle of the same size as the one you see on this page. In other words, it should have 2, 4, 6, 8 rows and 2, 4, 6, 8, 10, 12 columns. Oops. So that the clue is 15 country names. So instead of having multiple categories there, all the things that you find in there are country names. So for example, you can put the country name France at some point, like here. You can put Italy. It's up to you to choose the country name. but 15 country names should fit inside this grid. Okay, so that's question 2 for you to answer. Now, word search puzzles are two-dimensional. Okay, you have a grid, and then the words can go in various directions. Now, string searching in computer science and engineering is one-dimensional, but you can easily convert a two-dimensional word search puzzle to 1D, one-dimensional puzzle. Okay, so for example, I basically unroll the puzzle to make it one-dimensional. So for example, if I go in row major order, I write LEAGLEUROKRD, that's up to here, and then continue with the second row, POXWYARD, until I get to this O. Sorry, this O over here. And then the next row is IE. So I basically unrolled the two-dimensional puzzle into a one-dimensional puzzle. And all the words that go across the rows also exist in this puzzle. So for example, Jersey, which you see here, also exists here. But of course, the vertical words do not appear here. So I make a second one-dimensional version of this puzzle that is aimed at solving, finding the vertical word. So this one goes LPIHAWKV, then EOEN. So I go basically in column major order and put all the columns one after the other. So these two one-dimensional puzzles, if I look for words in them, according to the clues, then I can find all the horizontal words, either going forward in this version or backwards in this version. And all the vertical words, for example, dollar here, is shown here. Okay, I need to make two more versions, one-dimensional versions of this puzzle to cover the diagonal word. So one version will go V, K, E, W, F, G, A, Z, J, R, H, J, O, E, E, until I've covered all the diagonals. And then the fourth version will go L, E, P, A, O, I, G, X, E, H, L, W, O, N, A, and so on. So if I add those two puzzles, these four one-dimensional puzzles are equivalent to the original 2D puzzle. Okay, not quite equivalent. There's a subtle point that I'll discuss in a minute. So if you have, for example, a program that solves these one-dimensional puzzles, you can use it to solve a two-dimensional puzzle by simply inputting the two-dimensional puzzle as four one-dimensional puzzle, and then your program will look in those four versions of the puzzle to find all the words that you're looking for. So from this point on, our focus will be on, when we discuss the applications of word search and string search more generally, we can focus on one-dimensional because two-dimensional or even three-dimensional puzzles can be converted to one-dimensional quite easily. Now, because, as I said, word search puzzles tend to be easy, so there are more complex versions of them around. So this one in particular comes from a magazine. There's a grid, a fairly large grid, so it makes it a little bit more challenging to search. And the clues are sort of like crossword puzzle clues. So for example, the first clue says House MD's Robert. Okay, so you have to know something about House MD, the House, the TV series. And then Robert may refer to an actor in that series or a character in that series. And probably the last name of that actor or character is what you have to look for. Like a crossword puzzle, okay? And then the second clue says it makes its own blank. So how can you complete that statement? And then further down, 4 of the clues are deadly sins. So you have to find 4 specific deadly sins in this puzzle. The fifth element, and so on. So this is a little bit more challenging even than the USA Today version because it has a bigger grid, and also the clues are not as direct. So if you're looking for, units of money, number of things is pretty limited. You try dollar, you try cent, you try maybe euro and stuff like that. But here the options are a little bit more complicated. So this one is for you to practice if you're interested in these kinds of puzzles. There's nothing for you to do or report on this. This is yet another way of making these puzzles more challenging. This particular version is called the missing piece puzzle. So a play on word, the missing piece, P-E-A-C-E. So these are Nobel Peace Prize winners whose names appear in this grid, again in various possible directions. But one of the names is missing, and we are trying to identify which name is missing. But a part of the puzzle is not given, and you have to sort of fill out that part as well. So for example, take the name Hume. Okay, so you're looking for H-U-M-E, but because some letters here are missing, so here is an example, H-U-M-E. So perhaps this entry should be E. You can write down E, and then you complete Hume. But then maybe there is a Hume somewhere else, either completely shown or maybe, also incomplete. So it's not certain just because you have H-U-M here, there will be E here. Okay? Another example, Marshall. Okay, so I'm looking for an M with an A next to it. So M-A, but this is not Marshall. And this M does not have an A next to it. This M does not have. So I don't see an M. This M does have an A, but there's not enough room to spell out Marshall. Okay, so perhaps some of these missing entries must be used to spell Marshall. So let's look, for example, for 2 L's in Marshall. So here are 2 L's. Here are 2 L's. None of those are candidates for spelling Marshall. Here are 2 L's, but there is not enough space here. Okay. Where else do I have 2 L's? Okay, remember that Marshall may be the missing one. Okay, so I don't know. So basically, it's a little bit more challenging than the previous versions of word search puzzle. And I'm going to ask you to solve this word search puzzle, supply a missing name. So basically, send me an image of the puzzle after you have completed it and marked all the names. and then tell me which of those names is missing from the puzzle. So that's your question 3. Okay, so what is the problem of string matching? String matching is a problem in which we are given a data string with n symbols and a pattern string with m symbols. Typically, m is much smaller than n. And I want to find that pattern string in the data string, if it exists. Okay, so this is basically the one-dimensional version, one of the one-dimensional versions of the puzzle that we had before. And let's say I'm looking for the pattern string eagle. So we ask the question, does the pattern string eagle appear in the data string? So sometimes we just have, it's a yes-no question, whether it appears or not. This is like, for example, dictionary spell check. Is this word, which I have in my document, does it appear in a dictionary? Is it a dictionary word? In which case I accept it. Otherwise, I try to see what what spelling error I committed. What are the locations of all occurrences of the pattern in the data? So sometimes there may be multiple occurrences of the pattern, and I may be interested in finding the locations of the pattern in the data. So the simplest way to do this string matching or string search is the brute force or sliding window algorithm. Basically, consider all possible positions where the pattern might begin. And for each start position, you have to do up to m comparisons to see if there's a match. So for example, suppose I'm looking for eagle. So does eagle exist in the string beginning with the first position? So I do a comparison of E and L. They don't match. So the answer is no. Eagle does not start in the first position. Then I slide that window over by one position and say, does the pattern eagle appear in this data string beginning with the second position? E matches E, A matches A, G, L, E, and the answer is yes. So if I was asking just a yes-no question, I already found the answer. The string appears, the pattern string appears in the data string. If I want to find the locations of all occurrences, I have to continue. So I say there's an occurrence starting at position 2. So that's one of the answers. Then continue. Okay, eagle starting with the third position, no. Starting with the fourth position, no. And it turns out that this particular example, which came from the USA Today puzzle, there's just that one. But in general, that could be multiple positions. And the answer here would be all the starting positions of the various instances of the string eagle. The worst case complexity of this algorithm is order m times n, when n is the size of the data string and m is the size of the pattern string, because the starting position can be any one of the m, not quite m, not quite n minus m plus 1, because, for example, it cannot start here. 4 position from the end, because what I'm looking for is 5 letters. So this is the last position where it can start. So it's roughly n. Remember I mentioned that m is typically much smaller than n. So roughly n starting positions. And for each starting position, I have to do m comparisons in the worst case. Sometimes just one comparison is enough. And I see that eagle does not start in the third position. Okay, But in the worst case, I may have matches all the way up to the end, maybe not the last one. So roughly m comparisons per position. So that's order m times n. Now, if I have a very long data string and a moderately long pattern string, this can be a large number. It takes a long time to do all these basically probes or searches. Now, the data string can be huge. Okay, imagine that the data string is all the contents of the web, the World Wide Web. So all the documents in the World Wide Web with their letters, of course, documents also have images, formulas, so it's not as simple as this, but imagine that all the documents just have words and letters. String all of them together and you form this huge string that represents the entire content of the web. And then you say, okay, what are the web documents that contain the word eagle? Now, if you have to do this search n times, m times, even if m is pretty small, n is huge, okay? So this algorithm is not very fast or efficient. That's why it's called the brute force approach. Okay, I already mentioned that 2D search puzzles can be converted to 1D searches by doing row major unfolding. So here I've color-coded the different rows so that you see how they're placed. The first row is blue, the second row is orange, the third row is purple, and so on. Or I can do column unroll. Now, when I do this, something happens that is undesirable. That is, this word extra appears in the 1D version of the puzzle, whereas it did not exist in the 2D version. So this 1D puzzle isn't quite equivalent to the original 2D puzzle because there's this chance of additional words appearing that start in one row and end in the next row, whereas that's not a valid word in the 2D search puzzle. But this is easily solved by inserting a special character at the end of each row so that to break that continuity from one row to the next row, and therefore this word extra no longer appears in this version of the puzzle. So when I unroll the puzzle from 2D into 1D, I insert that special symbol, or any special symbol that is not part of a normal word, to break these spurious words, the words that do not really exist in the puzzle. Okay? And then I can unroll, as I said, in the column direction, column major order, or diagonal and anti-diagonal direction. Now these string search puzzles are sometimes referred to as finding a needle in a haystack. So the haystack is the huge data string that we have. The needle is that short pattern string that we are looking for. And, this sort of emphasizes that it's a hard job to find a needle in a haystack because you basically have to go to different points of the haystack and just look at each possible position, including the inside parts of the haystack. So it takes a long time to find the needle. It's a tough job. Okay, so here's an analogy. Search for the 10-symbol or needle, which is the name Helen Hunt, the actress. It's 10 symbols because there's a blank in the middle. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So find this string of 10 symbols in the internet, in the World Wide Web, which is our haystack. That haystack has many, many terabytes or even petabytes of data, okay? So it's huge. On the other hand, when you put Helen Hunt as your key for a search, say Google search, within a fraction of the second, the hits come back. You're told that these pages contain references to your string. And you may wonder, how is this done? Does Google actually go and search the entire web to find this string? Because it's going to take a long time. It won't be a fraction of a second that this for your response. It takes for your response to come back. Okay, so more on this later. The brute force algorithm does not work here because it basically says, look in this corner, now in this other corner, then over there, and so on. You look at every possible location. Of course, if the needle is made of metal and you have a magnet, then you can sort of cheat and just move your magnet around different areas and it will attract the needle. So it takes less work. So the internet holds more than one, in fact, right now it's many more than 1 trillion pages. And it's growing by billions of pages a day. Each page on average contains in excess of 10 kilobytes of data. So again, for simplicity, let's assume that we have just letters, text, simple text on the internet. So let's say the 10 letter string that I'm searching for, m is equal to 10. N, the size of the internet, is 1 trillion pages times 10 to the 4 bytes per page. That's 10 to the 16 bytes. As I said, right now it's much bigger than that. Or 10 petabytes, or 0.01 exabytes. And m times n will be 10 to the 17. So that brute force approach would require 10 to the 17 comparisons. Okay, and if we are able to do 10 to the 9 comparisons per second, a fast computer can easily do 10 to the 9 comparisons per second, then we need on the order of 10 to the 8 seconds, or 3 years, to do all of these comparisons, okay? So that's definitely not the method used by Google and other search engines to find the string that you're interested in. So here's an example of an internet search actually conducted on my computer. So I put Helen Hunt inside quotes in the search box and press search, and here is what comes out. And it says that there are 1,330,000 hits or pages on the internet that contain that string. And this happens within a fraction of the second. Furthermore, the pages that are more likely to have useful information, I'm searching for this actress, perhaps I'm interested in her biography or maybe the films she has made. Okay, so the most useful pages actually come first. So Google not only finds all those pages, but rank orders them according to what it thinks is the interest level in the pages. Okay, so here is Helen Hunt, and the Internet Movies Database. Here's Helen Hunt's Wikipedia page. Here is Helen Hunt at helenhunt.org. That may be her own private web domain. Okay, so you see that the most useful pages appear first, but then, 1 million, more than 1 million, there will be many pages coming later. Okay, actually I performed this search multiple times. So I did it again in 2009 and I got 2.1 million hits. I did it again in 2012. So as I was teaching this course, once in a while I went and redid the search to see what happens. In 2012, there were 5.4 million hits. And in 2016, 4 years ago, there were 42.1 million hits. That means, new pages were created during that period that have information, or at least the name Helen Hunt is mentioned in them. Now I did something interesting. I misspelled the name Helen Hunt. I put 2 L's in there to see what happens. Of course, such a person may not exist, but actually there were 735 hits for that misspelled name. So apparently a lot of people misspell that, and in their pages they have that, misspelled name. There are 735 such pages. But interestingly, Google asked me, did you mean Helen Hunt? So that it's suspected from the small number of hits that something is amiss here, and this is not what I really wanted to search for. And using information about the most common types of errors. So the most common types of typing errors are inserting an extra letter. So it basically goes and sees, okay, what if this H is the extra letter? What if this E is the extra letter? So it does multiple searches by removing one letter, because that's a common error that people make. Also, another common error is missing letters. So in typing Hunt, for example, I may leave out U and just type H and T. And then a third common type of error is transposition, where 2 consecutive letters appear out of order. Because when you type quickly, sometimes your fingers hit the keyboard out of order. So for example, I may type HNUT instead of HUNT. So Google tries those transpositions too, and then it sees that for this particular string, there are a lot of hits. So that's the basis upon which it thinks that maybe I was trying to search for this string and not the one that I actually typed. Okay, so we established that the brute force approach is not practical, and it's definitely, it's not what Google uses, because it would take months, sometimes years, to search the entire internet. So how does it do it? Well, there are a bunch of methods to reduce the amount of work when you search for strings, pattern strings within data strings. So if there is a particular pattern that you search for very often, let's say you do frequent searches for UCSB, okay, find information about UCSB. So that's a fixed pattern that you are interested in, but you want to search for it in different data strings. Then there is a method that allows you to do less work. the analog of magnetizing the needle. Okay? The converse, if your data string is fixed, so the internet. Of course, the internet is not fixed because it's changing all the time. But at a particular instance, the data string is, then you want to search for different things in that fixed data string. One moment you want to search for UCSB, and another moment you want to search for Harvard or some other string. Okay, that is done by developing indexes. Okay? So you make a thorough index of the haystack. You basically go through the haystack once and make notes, attach maybe post-it notes to different parts. Here is the part that contains this. Here's the part that contains this. And those indices basically help you in subsequent searches. So let me go into some details here. So example of pre-processing the pattern string. So I want to devise an efficient method for finding the pattern ABCBAB in various data strings that are formed from the symbols A, B, and C. So I'm sort of simplifying the problem. Instead of just, strings of English letters, I just take 3 letters A, B, and C. So I have various data strings that have A, B, and C in them. And then I'm interested in finding occurrences of ABCBAB in those strings. Okay, so I form what is known as a finite state machine. And I basically transition between states to remember what part of the string I've already found. So when I see an A, I've already found this part of the string. If after that I see a B, I've already found the string up to this point. If after that I see a C, then a B, then a B, then this is basically this notation, double circles, means that's the end of the string. I've already found that string. Okay, however, this may not go as smoothly as that. So for example, in the string, I can have a part that says ABC, then A again. Okay, so I found A, I found B, I found C, but instead of B following it in the string, in the data string, I have an A there. Okay, so that should take me from this state to this state, because that A is now the beginning of another string that is a possible candidate. So I can complete this state machine. I leave it up to you to study it and understand why those connections are made. Okay, so here's my data string, and I'm interested in finding in this data string occurrences of ABCBAB. Remember, the brute force approach required the product of the length of the data string and the length of the pattern string. This approach requires just the length of the data. So by just one scan of the data string, I can find all the occurrences. Okay? So instead of order m times n, it's just order n. So it's a little bit better. Although if the data string is huge, this is still not a satisfactory solution. So how do I do this? I start from the beginning of the data string. And I say, okay, I'm in state 0 at the beginning. When I see A, I go to state 1. Then in state 1, when I see B, I go to state 2. In state 2, when I see C, I go to state 3. In state 3, when I see B, I go to state 4. In state 4, when I see B, okay, that string contains A, so I'm not making progress there. If I see B, I go all the way to the beginning and start over. So I go to state 0. Then in state 0, I see B. I remain in state 0, okay? Because B does not start what I'm looking for. Then I see A, go to state 1. I see B, go to state 2, state 3, state 4, state 5, state 6. So I found the first occurrence of A, B, C, B, A, B. And then mark that by writing the number 6 in red. And then in state 6, I see a B, so I go all the way to beginning and start over. C, A. So I see an A, I go to state 1. In state 1, I see another A, okay, this A. So I remain in state 1 because now that A can be the start of the string. B, C, B, A, B. And that's the second occurrence of ABC, BAB. Now from this state, if I see C, I go to this state. I don't start over. The reason being that AB, which is the end of this string, can also be the beginning of the next instance. So from state 6, when I see C, I go to state 3. Then B takes me to state 4, state 5, and this is the third occurrence. Notice that the two occurrences are overlapping. So here is one ABCBAB. Here is one ABCBAB, and the two overlap, and this approach actually found both of them. All right? So I identified all three occurrences of the pattern string ABCBAB by just traversing the data string once from beginning to end. There was no repetition involved, okay? Each symbol was examined just once with the help of this state machine. Okay, now here is the more interesting example, and this is what happens in search engines. We pre-process the data string. So Google and other search engines have programs that are called bots or robots. They sort of go visit various websites, and before you even search for anything, you know, continuously, that's their job. Continuously, they're looking at different websites and make indices that tell the search algorithm, okay, what those pages or sites contain. So for example, in the case of the same situation where the data string is just contains A, B, and A's, B's, and C's, and the pattern string is again A's, B's, and C's, and imagine that this string is the entire internet. So at its leisure, Google sends these bots to various websites, and then they sort of make note that AAB, so they take three-letter strings, AAB, okay, appears here in position 14. So in this string, there's a position. In the case of Google indices, that would be a website address. Okay, AAB exists in that particular website. Okay, there's just one occurrence at location 14, so the index is constructed accordingly. ABB starts at location 10, there's just one occurrence. ABC, there are many occurrences, starts at location 0, starts at location 6, starts at location 15, and so on. So all these possible triples of letters that are found, they're entered into this index. So this index is a huge database that Google maintains on its servers. And now if you go and search for a particular string, okay, so you put ABCBAB in the search box, okay, Google already knows where all the ABCs are. Here they are. And then it also knows where all the BABs are. Here they are. And then if you want to have this string, the location of ABC should be 3 less than the location of BAB. So if this is at location 10, 11, 12, 13, BAB should be at location 13. Okay, so you look among these numbers to see which pair has the difference of 3. 6 and 9 satisfy that. 0 and 5 do not. 0 and 9 do not, but 6 and 9. 15 and 18. 19 and 22. So this tells me that there are 3 locations for the string ABCBAB, starting at location 6, 15, and 19. Sure enough, here's ABCBAB, starting at location 6, and 15 ABCBAB, and 19 ABCBAB. Okay, so when you do a search, Google does not just wake up and say, okay, let me go search the web. It has already searched the web ahead of time and has prepared this index. All it has to do when you supply your search string is to consult this index and do some minimal computation, okay, to find out where that string exists. And then typically this will be the website. It gives you the website and some characteristics of the website and sample a little bit of the contents and so on, so that you know whether you're interested in that particular website. Okay, so here is question 4 for you to answer. Use the index above to find the locations of the string BABC in the data string. Okay, so I showed you how ABCBAB would be found. Now you tell me, by specifying the steps of the algorithm, how you would go about finding BABC. There's more than one way of doing it, so just use your intuition to see how that should be done. Okay, here's another pre-processing example. It's known as a suffix tree. So suppose the data string is Mississippi. Okay, this is a small example. And we put a $sign at the end, so that that's sort of a signal that that's the end of the string. So whenever we scan the string, when we get to the $sign, we know that that's the end of it. That's a unique symbol at the end of the string. Okay. So I construct this tree based on the suffixes of that string Mississippi. Okay. So this is the full suffix, the entire that takes me there. Okay. There is a suffix of the string which is $. Okay, that's $. There's another suffix $. So that's the one, $. And there is yet another one, ISSI $, ISSI $, and finally ISSI $, ISSI SSIPP. So the paths on this tree are all the possible suffixes of the data string with sharing done. So all the suffixes that begin with I basically are here. All the suffixes that begin with dollar are here. These letters should have been written closer to. So there's just one suffix that begins with dollar. That's the one. All the suffixes that begin with P are in that branch. And those suffixes are PI dollar, PPI dollar. So this is PI dollar and PPI dollar. And suffixes that begin with S are that final branch. So once you have constructed this tree based on the suffix tree based on your data string, it's pretty easy to see whether a particular string exists. Because any string that you are interested in, so for example, the string, let's say SSI, that will be the beginning of a suffix, okay? So suppose I'm interested in finding the substring SISS. SISS. Okay, that suffix starts with S. That string starts with S, so I look for a suffix that begins with S. Then it continues with I. Then with two S's. So this one has two S's, and therefore that particular string exists. It's part of the suffix SISSIPPI dollar. Okay. What about pi? Okay, pi starts with P, so I go in this branch. I. Okay, there's no I there. There's I dollar, but I don't have I dollar in the string I'm searching for. Okay, so there's no I. So at this point, I conclude that that string PIE does not exist in this data string. Okay, so I do some initial work to construct this suffix tree. But then whatever string I want to search for is very quick. In the worst case, I have to take as many steps as there are letters in the string that I'm searching for. Okay, so a few other interesting examples and we'll be done. So, I decided to search for the word the, THE, knowing full well that, many documents contain the word the. In fact, perhaps almost every document has it. So I try to see what happens. When I search for the word the, I found 5,290,000 hits. Actually, that number increased in subsequent searches until in 2016, there were in excess of 25 billion hits. This is, of course, because the size of the World Wide Web, the internet grew in the interim. Okay, and then what are the top hits for the Onion, the satire newspaper is the first hit. The White House is the second hit. Okay, so Google has some algorithm for deciding, among these billions and billions of pages, which one are more likely to be useful to the person who did this search. Of course, I didn't know that I did a random search. I wasn't really interested in finding any document. Then I decided to enter something random. So I just pressed my keys randomly and it came to XMZT. I was pretty sure that, this random string of characters does not appear anywhere. But to my surprise, there were 667 hits for that seemingly random string XMZT. And then Google actually asked me, did you mean KMZT? So the first time I did this, I wondered, okay, why is KMZT any less random than XMZT? Okay, think for a second and see if we can come up with the answer. I will reveal the answer. That's actually a radio station, KMZT. Radio stations on the West Coast, the codes begin with K, and MZT is for Mozart. That's a radio station that plays Mozart music, and there are a lot of hits. But the search actually was performed for XMZT. So these are some of the hits for XMZT. They're all Chinese sites, so I have no idea what XMZT means or why it is significant that it appears in these sites. So here's the site www.xmzt.cn in China and so on. So you learn a lot of interesting things by doing just random searches on the internet, as these examples. And then in the same example, in 2016, the last time I did this search, the number of hits had increased from 667 to more than 24,000. So even that random character has appears, the random character string appears in many websites. Okay, the final slide that I'll show you is the notion of approximate string matching. So this is done, for example, in DNA sequence matching. So as I mentioned, when you commit an error in writing down a string, the most common human errors are of these types: inserting an extra character, missing or dropping a character, or transposition. And then therefore this leads to basically ways of trying to guess what you meant when your search does not return many matches. Okay, so I'm going to skip the rest of this slide and show you the next slide, which is a bit more interesting. So this is basically DNA sequence alignment problem. So basically you have, let's say, DNA evidence from somebody who committed a crime, and there's a database of DNA samples, information of people, for whom we have DNA, usually, felons whose DNA samples are taken. And then you want to see in that database, what is the closest match to this? So the DNA string consists of a sequence of 4 letters, A, C, G, T. So this DNA sample, so this is a small sample, okay? Typically these are much longer. A, G, 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 C, T. And this is an entry in the database. And I'm trying to figure out how close these are. Of course, they don't match exactly. I'm interested in finding the closest match, okay? So this is how that can be done. This similarity between two DNA sequences occur because letters are missing or they are mismatched. So for example, if I align these two sequences the way I've shown here, there's a match in A, there's a match in G, there's a match in this G, there's a mismatch, and there is a missing or gap missing entry. So the total dissimilarity between these two is a GC mismatch, a CA mismatch, and one gap. Okay, let's now align the two differently. I say, okay, maybe this sequence is missing something here. Okay, so I align it like this. Now I have match, 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 gap, match, a TA mismatch. Okay, so the mismatch has been reduced. In both cases, I have one gap. In this case, I have just one mismatch. And in this case, I have two mismatches. And of course, I can assign different weights or importance to various mismatches. So if all mismatches are the same, then this is definitely a better alignment because it has one mismatch versus two mismatches. But if this mismatch is considered more important, then perhaps this. So if this mismatch has weight 2, but each of these have weight 1, then the two solutions are the same. Okay? All right. So that's it's very difficult to find optimal alignment, and there are algorithms called dynamic programming that help us solve this problem with less computational effort than a brute force search. Okay, so that's all I wanted to say. Please remember that this was lecture 8, scheduled for Monday, May 18th. And your attendance report is due by Wednesday, May 20th at 6:30 p.m. All right, stay safe, and I'll see you in the 9th lecture, which is going to be actually our last lecture, because normally we have 10 lectures for this course, but one of the lecture dates, the Monday of Memorial Day observance, we won't schedule a lecture, so the next lecture will be the last one. Okay, bye, and thank you.